Good morning all. This is Dr. D. Khalandar Basha, working as Associate Professor in the Department of Electronics and Communication Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss the interfacing memory with 8051 microcontroller under the course Microprocessors and Microcontrollers. The slides are prepared by referring the textbook The 8051 Microcontroller by Kenneth J. Ayala, publication Flickr Link. So in 8051 microcontroller, apart from the processor, we have on-chip ROM as well as on-chip RAM apart from the peripherals. So the 8051 microcontroller, on the chip we have 4K bytes of internal program memory, that is code memory, which you can take as ROM, whereas 128 bytes of memory for storage of internal data, which is a RAM. So for any application, if the size of the ROM or RAM which is existing on chip is not sufficient, then we go for extending the memory for 8051 microcontroller. So to interface a memory chip to the microcontroller, the following signals are required to be generated. So this is microcontroller, and here we have memory block. We require the address lines. We require the data lines either for read or write operation. Apart from that, for enabling the chip select lines, we are going to take the chip select lines. Next, a read and write control. If it is ROM, we have only read permissions. If it is RAM, we are going to have both read and write access. However, the chip select will be enabled by means of the address lines only. The signals that are mapped in 8051 microcontroller environment are the address and data lines are provided alternative functions for the ports port 0 and port 2. These pins will act as both port pins as well as address and data lines. The port 2.0 to port 2.7 bits constitute the address lines for upper 8 bits, that is from A8 to A15. We can call this one as higher order address lines. The pin numbers for port 0 to 0 bit to port 0 7th bit represents both data as well as address information, that is AD0 to AD7. This will have both address information as well as data information. When ALE is equivalent to 1, address will be placed on these lines. When ALE is equivalent to 0, data will be placed on these lines. So in case of 8086, an external latch will be required to latch the byte when it is present. The memory chip select signals are obtained by decoding the address information through a decoder. For external data memory, the read signal which is on port 3.7th bit and the write signal which is on port 3 6th bit are used as read and write control signal. So for ROM, we require only read signal, whereas for RAM, we require both read and write signal for accessing the memory. Now we will see the interfacing of the memory to the 8051 microcontroller. So first we will take the external ROM, which is a program memory interfacing. So from 8051 microcontroller, port 0 is used for the data access for this ROM. Next, this ALE signal, it is for differentiating address lines and data lines. Next, we have the upper 8 bits, that is from A8 to A15 will be passed. As it is a external program memory, in this memory block, the output enable OE bar is connected to the PSEN bar signal of the 8051 microcontroller, which is program store enable. Next, as it is an external memory, for accessing the external memory, we are going to replace the EA signal is active. As it is active low signals, we will connect this one to ground whenever we want to access the external memory. The figure shows how to access or interface ROM to 8051 microcontroller. Port 0 is used as multiplexed data and address lines. It gives a lower order, that is from A0 to A7 address 8-bit lines in the initial clock signal, and the higher order address lines, that is from A8 to A15, are used as the address lines. The 8-bit address is latched using external latch, and ALE signal address latch enable signal from 8051 microcontroller. Port 2 provides the higher order, that is A8 to A15 8-bit address lines. The PSEN bar, this is program store enable signal, is used to activate the output enable signal of external ROM, that is our APROM. Now we will see the external interface if it is for RAM, that is for data memory. Here the port 0 is connected to the data lines from D0 to D7, as well as this is connected to A0 to A7. So what are the information which you are having on port 0? Either it may be data or it may be address. So this will be enabled by using the ALE signal. When AL is equivalent to 1, the latch will be transparent so that the data will be passed on A0 to A7. However, the upper lines we are going to have on A8 to A15. Next, here we have the read signal and the write signal, which are there on the port 3.7 and 6 for read and write operations connected to write and read operation corresponding bits of RAM. So the figure shows how to connect or interface the external RAM, which is a data memory, to 8051 microcontroller. The port 0 is used as multiplexed data and address lines, that is from AD0 to AD7. The address lines are decoded using external latch and ALE signal, that is address latch enable signal from 8051 microcontroller, provides the lower order address lines, that is from A0 to A7. Port 2 gives the higher order address lines, that is from A8 to A15. The read bar and the write bar signals from 8051 microcontroller selects the memory for read operation and write operation respectively. The read bar and the write bar signals, these are generally connected to port 3.6 and 3.7 pins for the port 3 and are used to generate the memory read and memory write signals. The remaining port pins, however, the port pins of 3, that is P3.0 to port 3.5 bit, are used for other functions. Next, for decoding the address information, we have two kinds of decoding mechanism, linear and absolute decoding. In the absolute decoding, all the higher order address lines are decoded for selecting the memory chip for specific logic levels. So if I have a memory, out of these 15 address lines, so let us consider you require from A0 to some AX lines, X number of lines. So then these lines are used for address for accessing one of the memory location. The left out, that is AX bits to AN-1 bits, these are used for the decoding purpose. For other logic levels, memory is disabled. This absolute decoding usually used for large memory systems. The figure in the next slide shows the memory interfacing using absolute decoding. So now in this address lines, that is from A8 to A13, we are using as it is a 16K. 16K memory means 16 we can write as 2 to the power of 4. 1K is 2 to the power of 10, that is 2 to the power of 14. So 14 address lines are required here. These 40 lines are A13 to A0. So these address lines are used for accessing the any one of the memory. What about remaining signals? So the left out signals are A14 and A15. These lines are used for the decoding purpose. As it is a external memory, whenever accessing the external memory, the external bus will be connected to ground signal, that is VSS. Port 0.0 to port 0.7 provides the address and data information on AD0 to AD7. The ALE signal will make the latch as transparent for T1 cycle to pass the address information. So the address lines which you require is A0 to A13, out of which A0 to A7 are covered. The remaining address lines, that is A8 to A13, are used the remaining address lines for accessing the memory. However, the A14 and A15, these lines are used for selecting of the chip select. Some logic you can apply for selecting the chip select. So whenever you program these bits as some logical operation such that this data has to provide is 0, so that the chip select, which is a active low signal, will be enabled. So apart from that, P3.6 and P37.5 are 3.7 are for write and read signals respectively. Here PSEN bar is not used as it is not a program memory. The next kind of decoding mechanism we are having is linear decoding, which we can also call as partial decoding. So this mainly used for small systems with memory size. Individual higher order address lines are used to select memory chip. It reduces the cost of decoding. The drawback of linear decoding is multiple addresses. As shown in the figure in the next slide, A14 line is directly connected to the chip select line. The A15 is not used. So the status of A15 is not considered to generate the chip select signal. So in this linear coding, here also we are considering 16K. So this 16K means 2 to the power of 4 into 2 to the power of 10, which is 2 to the power of 14. So 14 address lines are required. Out of these 14 address lines are, that means A0 to A13 are used for accessing the memory. So A0 to A7, A8 to A13. So what are the address lines are left out? A14 and A15. So instead of using two address lines, we will select only one address line for differentiating whether it is ROM or RAM memory. So that will be used for connecting the chip select. P2.6, which is nothing but A14 line, is used for connecting the chip select. What about A15 is? A15 is unconnected. Next, the PSEN bar, which is a program store enable, as it is a RAM, this is also not required. As it is RAM, we require both write permissions as well as read permissions. Now in the address mapping, we can say that the address lines from A0 to A15, which are X address denoting the address, are required. In the absolute decoding, let us assume the memory size which we are taking is 16K. As we know, for 16K, we require 14 address lines, that is A0 to A13. So from A0 to A13, we used for accessing the memory. The A14 and A15 lines are used for decoding purpose. So as it is a absolute decoding, we have to use all the address lines. So by providing 00, we are taking it is a chip select for the RAM, which are the memory block which are taken. So the starting address for this one we can have is 0000H to 3FFFH. Whereas in the linear decoding, for the same 16K memory, A13 lines are required. A0 to A13, that is 14 address lines are required. A14 is used for chip select. How about A15 is, it is a don't care. So only we are going to use these lines. Here you can have either 0 or 1. So the addresses from 0000H to 3FFF. Here in this example, the X value we are taking as 0. But it can be changeable for 1 also. Then I'll get this is 1, this is also 1. Then my address will become 8000H to 1011 BFFFH. This is the address map in that case. So now we will see the comparison between the full address and partial address, which is nothing but absolute decoding and linear decoding. So in absolute decoding, all the higher order address lines which are not used for accessing the memory, these address lines are used for decoding to select the memory or IO device. Whereas in the partial address, only few or individual address lines are decoded to select memory or IO device. In the absolute decoding, the decoding mechanism required more hardware, whereas in partial decoding mechanism, the decoding logic will require less hardware. As the hardware is complex in absolute decoding, usually the cost of the decoding system also will be high. Whereas in partial decoding, the decoding circuit will cost less. In the absolute decoding, as we are using the entire address lines, so no multiple address will exist. Whereas in the partial decoding mechanism, as we are left out few address lines, so multiple addresses can be possible. The absolute decoding will be used generally for large systems of memory, whereas partial address decoding will be used for small systems. Now we will see few problems related to memory interfacing. Design a microcontroller system using 8051 microcontroller. Interface the external RAM of size 16K by 8. So in any general memory, if the memory is consist of 2 power n memory locations, it indicates it requires n address lines, and each location may consist of m number of bits that will corresponding to the data bus. So for this kind of memory chip, as it is consist of 2 to the power of n number of memory location, each memory location size is 8 m bits, then the memory will be represented as 2 to the power of n cross m bits. So this 2 to the power of n will be based upon the address lines. This m will be depends upon the data lines. Now in the problem, the given memory size to interface is 16K. So that 16K we will represent in terms of 2 to the power of n. We will find out n, where n will specify the number of address lines. So the 16K we can write as 2 to the power of 4 into 2 to the power of 10, which is equivalent to 2 to the power of 14, which indicates the 14 address lines are required. For accessing the memory, 14 address lines are required. The address space in 8051 microcontroller is A0 to A15. Out of these 16 address lines, we require from A0 to A13. So A0 to A13 are used for accessing the memory, whereas the left out A14 and A15 are used for using some OR gate or AND logic function for enabling the chip select of RAM. So when when A14 address line 14 and 15 are low, then the external RAM is selected. So address decoding map for 16K into 8 RAM we will see. So in the address mapping, so total A0 to A15, 16 address lines we are taking, out of which A0 to A13 are required. So in each and every memory location, we will pass the minimum value as 0 and the maximum address will be generated by passing each and every bit is equal to 1. So only from A0 to A13 are required. A14 and A15 are used for decoding purpose. This is for addressing. So this A14 and A15, we can pass any one of the value, either 00 or 01, 10 or 11. Let us assume if A14 and A15 are taken as 0, so the address map for this case is 000. Every 4 bits will combine 0, 0000, 0, 0, 0. So the starting address will become 0000H. Whereas the higher address is 0011, which is 3, 1111, that is F, 1111F, 1111F, that is 3FF. So the address space for accessing the 16K memory block is 0000H to 3FFFH. So the interface diagram we can see, which is for interfacing 16K by 8 RAM. So port 0, it is used for address and data lines for A0 to A7, whereas the port 2, as we require only 14 address lines, A8 to A15 will be used. So the A14 line and A15 line are used for selecting the chip select. However, as it is a RAM, we are going to have both read signal as well as write signal as the control signals for read and write signal, write operations. Next, we will see the second example, where in the second example, we are going to design a microcontroller system using 8051. Here we are going to interface an external ROM of 4K by 8. So here the memory size is only 4K. So 4K means we can write as 2 to the power of as 2 to the power of 2 into 2 to the power of 10, which means 2 to the power of 10 plus 2, which is 2 to the power of 12. So we require 12 address lines are required for accessing any one of the memory. That will take from A0 to A11. The upper address lines, that is A12, A13, A14 and A15 are used for the decoding purpose. This is for address for memory access. A0 to A11. So given memory is 4K locations, where 4K we can write as 2 to the power of 2 into 2 to the power of 10, which is 2 to the power of 12. 12 address lines are required, that is from A0 to A11. The higher order lines, that is from A12, A13, A14, A15, these lines are used for enabling the ROM. However, as we want to write the code into the ROM block, we have to enable the chip select, PSEN bar, which is program store enable signal. So whenever we want to write the program into the ROM block. Next, the A0 lines, the address lines A12 to A15 are low. Only the external ROM is selected. The address decoding map for 4K by 8 RAM we will see in the table in the next slide. So here, as it is a 4K address lines, we know that A0 to A11 are required. The upper bits A12, A13, A14, A15, we can give any combination starting from 000 to 1111. Any combination we can give. So in this example, we are considering all the upper bits as 0. So then the address space for this one is 0000, 0. Every 4 bits we are going to be grouped as one hexadigit, right? 0000, 0, 1111, which is F, 1111, which is F, 1111, which is F. So the address space here it is 0000H to 0FFFH. This is the address space for accessing the memory of ROM, which is of size 4K. So now we will see the figure for interfacing. So the A0 to A7, which are multiplexed with the D0 to D7, which we are getting on port 0.0 to port 0.7. So for differentiating, it is address lines, the ALE signal will be given. The required higher address lines is from A8 to A13. So the left out address lines, that is from A12, A13, A14 and A15, these are used for generating the chip select lines. As it is ROM, we are not having any write signal for ROM. The read signal will be connected to the read signal of this as well as apart from PSEN bar, which is program store enabled signal. Next, we will see the next example, which is design a microcontroller system using 8051. We want to interface some memory blocks, which is of 16K bytes of ROM and 32K bytes of RAM. Interface the memory such that the starting address of ROM is 0000 and the RAM is 8. So if you observe the higher address lines 0 means we are going to be use the unused address lines with 0, whereas if you see the upper 4 bits 8 means we are going to have the configuration is 100. So left out bits will be configured according to this address. Now the given ROM size is 16K, which means 2 to the power of 4 into 2 to the power of 10, which is 2 to the power of 14. 14 address lines are required. That is from A0 to A13. How about A14 and A15? These are used for decoding mechanism. As the starting address, if you observe the upper bits, they are 0. So usually you take A14 and A15 as zeros. When it comes to RAM, the RAM size it is given is 32K, where 32K we can write as 2 to the power of 5 into 2 to the power of 10, which is equivalent to 2 to the power of 15. So 15 address lines are required. So that is from A0 to A14 will be used for address generation, whereas A15 is left out for decoding. If you observe the RAM decoding address is started with 8. 8 means the upper bit is always 1. So in this case, we are going to take A15 as 1. So given ROM is a 16K, that means we require 2 to the power of n, which is equivalent to 16K, where n is the number of address lines. So in this case, n is equivalent to 14. So A0 to A13 lines are used for accessing memory, which belongs to ROM. A14, A15, PSEN are used for chip select line. When A14, A15 and PSEN bar are low signals, then the ROM is selected. When it comes to RAM, the size of the RAM they are given is 32K. That means we require 2 to the power of n is equivalent to 32K, where n is the number of address lines. So in this case, the n value, that is 15 address lines are required, which will take from A0 to A15 out of the 16 address lines. Whereas A15 is used for enabling the memory block, that is chip select for the memory block. So when A15 is high, we are going to select the RAM, because in the address map they are given 8000 around it has to be exist. So we'll take A15 as 1. So the PSEN bar, which is program store enabled, is used to chip select for ROM, whereas read and write signals are the control signals for read and write the data to the RAM block. So the address mapping for ROM block, and this one is for RAM block. So the address space here we are going to select for ROM is A0 to A13. Total 14 address lines are required for accessing. However, the upper bits are 00. So the address space for this one is 0000, that is 0, 0000, 0, 0000, 0, 0000. So the starting address is 0000H. Whereas the upper address is 0011, which is equivalent to 3, 1111F, 1111F, 1111F. So the upper address is 3FFFH. Whereas for 32K ROM size, we require A0 to A14 lines. So we'll place each and every bit with the minimum value as 0 and maximum address will be generated by writing each and every bit is equivalent to 1. So A15 we are going to be write as 1 as the given address space is 8000 around. So A15 will take as 1. So the address space for RAM is 1000, that is 8, 0000, 0 and 0. So the starting address is 8000H. Whereas higher address, if you see all the bits are 1, so it is FFFFH. So the address space for ROM is 0000H to 3FFFH. Whereas for RAM, it is 8000H to FFFFH. So this is the interfacing diagram for a 16K ROM and 32K RAM. Next, we will see a design microcontroller system using 8051, 8K of ROM. So ROM size is 8K, 8K of data, that is RAM is 8K. Interface the memory such that address space for ROM is 000, whereas for RAM is E00. So E pattern, what is the E value you'll get is 110. So whatever the left out bits are there, this we have to write according to this pattern. So as we see in both the cases, the size of the memory is only 8K. So 8K means this we can write as 2 to the power of 3 into 2 to the power of 10, which is 2 to the power of 13. So 13 address lines are required. So these address lines we will take from A0 to A12 address space. So what about the remaining address lines, that is A13, A14 and A15. These are used for accessing the memory for decoding mechanism. We will use these address lines. So given the memory size, here it is for RAM 8K, such that we require 2 to the power of n, which is equivalent to 8K, where n is the number of address lines. So in this example, n will become 13. So we are going to take A0 to A12 address lines for accessing. The address left out address space, that is A13, A14, A15, PSEN bar, will be used for chip select. As it is a ROM, we are going to be include PSEN bar. So when A13, A14, A15 and PSEN bar are active low, then the ROM will be selected. Similarly for RAM case, the memory size it is given is 8K. So it requires 2 to the power of n is equivalent to 8K, where n is the number of address lines. So in this case, n will become 13. So we will use A0 to A12 address space for accessing the memory. The left out address lines, that is A13, A14, A15 are used for selecting the chip select. So when A13, A14, A15 are high, the data RAM is selected. However, the PSEN bar, that is program store enable signal, is used for selecting the ROM block, whereas write and read control signals are used for RAM signal. So the address space we are going to take for 8K is A0 to A12 are required, that is 13 address lines. The upper address, as the given specification, the address for ROM is 000 something, whereas for RAM it has to start with the E00. So for that purpose, we are going to give the upper lines as 0 for ROM, 111 for RAM. So the address generated for the ROM block is 0000, that is 0, 0, 0, 0. So the starting address is 0000, whereas the upper address is 0001, that is 1, 1111F, 1111F, 1111F. So the address space is from 1FFFH. Whereas for 8K RAM block, here we require A0 to A13, A13, A14, A15 will be used for decoding mechanism. So here the bit configuration is 1111, 1110, which is equivalent to E000. So the starting address is E000H, whereas upper address is each and every bit is 1. So we are going to have all the bits as 1. We'll write the upper address is FFFH. So here why we are selecting the A14, A15 as 1 means, here we are going to select according to this address space which is given. ROM is given with 000, whereas for RAM it is given as E000. E equivalent is 1110. So this IARE address bit always should be equivalent to 1 for RAM case. Now the interfacing diagram looks like in the figure shown. 8K ROM, 8K RAM. The address map, both are having the same address space, that is A0 to A7 followed by A8 to A12. The remaining address lines, that is A13, A14, A15 are used for chip select. For ROM block, we are going to include PSEN bar for decoding mechanism. Whereas for this, we require only A13, A14, A15 for selecting chip select. However, read bar and write bar signals are given for enabling the memory access for both read and write signals. As these two are external memory, always we have to connect EA, that is external access, is equivalent to 0, which is nothing but VSS. Now we will see what is the maximum memory we can interface to 8051 microcontroller. One case will take as only single block, either you may have RAM or ROM. Whereas second case will take two memory chips of equal size. RAM some X amount of memory, ROM is some X amount of memory. As we have seen in 8051 microcontroller, the number of address lines are 16 address lines. That is from A0 to A15. As we have a 16 address lines, so the maximum memory we can access is 2 to the power of 16, which we can write as 2 to the power of 6 into 2 to the power of 10. 2 to the power of 6 is 64 and 2 to the power of 10 means 1K, which we can write as 64K. If I have a single memory block, then the maximum memory we can access is 64K. So a maximum of 16 for ROM and RAM combinedly we can interface for the 8051 microcontroller. If we have a single memory chips, what is the maximum size we can have is 64K. If two memory chip of equal size, then we are going to take 32K plus 32K. Now we will see in the first scenario where we are going to use the external pin. Here we have both ROM internally and externally. Say internally we are going to have a 4K, externally we can have the maximum address space is 64K. Now in this case, the address we are going to take from 000H to 0FFH, whereas the next address is from 100H to FFFH. So as we want to access only the internal memory, we will connect the EA pin to power supply. When EA pin is connected to plus 5 volts, that means the external access will be disabled, so we can't access the external memory, only internal memory will be accessed. So in case of 4K of internal ROM, the address space is 000H to 0FFH. If the address space, that is program address, exceeds this value, then the CPU will automatically fetch the code from the external program memory. For this, the external access must be pulled to high. That is, when external access pin is at high, the CPU first fetches the internal program memory, that is from the address 0000H to 0FFFH. If the program memory is in the address exceeds the limit, then the instructions are fetched from the external ROM, that is from 1000H to 0FFFH. Second scenario is when EA pin is connected to ground. In the EA pin is connected to ground, that indicates the external access is enabled. So when external access is enabled, we can't access the internal program memory. The entire external memory we can access, that is from the address 0000H to FFFH. So there is another way of fetching the instructions. Ignore the internal ROM and fetch the instructions from the external program memory only. So in this scenario, the external access EA pin must be connected to ground. So in this case, the memory address for the external ROM is starting from 0000H to FFFH. Now for accessing the external memory content, we use MOVX instruction. The MOVX instruction is used to external data memory. So we will write move R0 comma some external address, then we'll write MOVX A comma at the rate of R0. So now we are going to access the external memory that content will be placed into accumulator. Otherwise, we can go for moving a DPTL with external high address, move DPH with external address low, then we'll write move X A comma at rate of DPTR. So either passing through R0 register or through DPTR register. So in this session, we have discussed the need of external memory for interfacing 8051 microcontroller, even though internally, that is on-chip memory is existing in 8051 microcontroller. So how to interface, what are the decoding signals we have to conserve for various memory blocks. Then for interfacing the 8051 microcontroller with the RAM alone, ROM alone, then combination of both RAM and ROM also we have discussed. As well as we are addressed to two decoding mechanisms, that is absolute decoding and the one is partial decoding. Later we have discussed the significance of EA signal. When EA signal is equivalent to 1, how the memory will be accessed with respect to external memory. If EA signal is equivalent to 0, how the memory access will be done for internal memory and external memory. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.